So I hope you are done with alcohols. Now we would start with ethers. Alright, so we are starting off with ethers. Alright, so let me write down the general formula for ethers. ROR dash, for example, CH3O CH3. This we call as dimethyl ether. C2H5O CH3, ethyl methyl ether, C2H5O C2H5 diethyl ether. Right. So these were examples of aliphatic alcohols. Now let's take up pH stands for phenyl ring. Alright, so let me draw the phenyl ring for you. So this is methyl phenyl ether. This is diphenyl ether. Alright, fine. Okay, so what is the general name of methyl phenyl ether? I hope you know this. This is anisole. Okay, fine then. Moving on to the physical properties of ethers. Physical properties. As it is very evident from the structure of ethers, okay, that the dipole moment in this case cannot be equal to 0. So this is the resultant dipole. These are the two dipoles which add up to this vector. So ethers do have dipole moment. Mu is not equal to 0. Alright, so one of the major physical properties of an ether is that these have dipole moment. Due to this dipole moment, they have considerably high boiling point than those that do not have dipole moment in them, as in the case of hydrocarbons. Of course, these ethers have less boiling point than that of carboxylic acids and alcohols. Alright, because in the case of carboxylic acid and alcohols, they have dipole moment supported by hydrogen bonding. So this hydrogen bonding elevates the boiling point of the carboxylic acid and the alcohols to a very great extent. Alright, so this has a dipole moment which tries to increase or increases the boiling point up to some extent. Alright, but not as good as the case of alcohols or carboxylic acids. Alright, fine. Now these alcohols, these ethers also form hydrogen bonds with those of water molecules, as this. Okay, so one ether molecule attaches to another hydrogen bonding via hydrogen bonding through only one site. So one ether molecule can have only one hydrogen bonding site. Alright, hope it's very clear from the diagram shown. Okay, so this oxygen has no in this ether we have no other oxygen that can combine with any other hydrogen. Alright, okay, fine. So just moving on to preparation. Preparation of ethers. Alright, so a very famous reaction known as Williamson's reaction is used in the preparation of ethers. Right, so let me write down the general reaction of Williamson's. You can visualize this reaction as this NaX is removed and this RO minus and this RO plus is attached to form the ether. Alright, so we have the sodium salt of any alcohol and an alkyl halide that takes part as the major reagents of Williamson's reaction or Williamson's ether synthesis. We have an alkyl halide and an alkoxide, sodium alkoxide. Alright, the sodium salt of the alcohol, ROH. When ROH reacts with Na, we have RONA plus half H2 liberated. We have seen these reactions earlier. Alright, so when an alkyl halide reacts with a sodium alkoxide, we are left with a ether. Alright, plus the sodium salt. Alright, so let's take up a specific example first, then we'll move on to the mechanism. So let's take, like, we have CH3Cl plus NaCH2CH3. So what do we get? We get CH3CH2, sorry, I forgot to write the O over here. So we get CH3O CH2 CH3 plus NX. So when methyl chloride reacts with the sodium salt of ethyl alcohol, we get methyl methyl ether and NaX or NaCl to be more specific. Alright, fine. So now let's see what actually happens in Williamson's reaction. Right. So in the initial case we have a nucleophile RO minus. We have a nucleophile. We have an alkyl halide, which is the substrate of this reaction. The substrate of this reaction. What happens is that this O minus attacks the substrate. Alright, this X leaves as X minus, so we are left with ROR plus X minus. So this is a nucleophilic is the nucleophilic substitution reaction. Alright, so we have this nucleophile RO minus. It attacks the substrate, alright, at R. So this X minus leaves. This is what we are left with, the ether. So this X minus combines with the Na that we are left with over here. Okay. So I hope you understand this. From the previous lectures on nucleophilic substitution reaction, we can tell that this is SN2 reaction. Okay.